Practice problem number 8. It says, what is the volume? Volume equals what? I'm just going to write everything down in columnar form. We'll go from there. What is the volume of 32.2 grams of chlorine gas? What's the molecular formula for chlorine gas? (32.2 grams of chlorine gas. I'm going to write chlorine gas up here. What's its formula? Cl2, right? Because it is a homonuclear diatomic, right? So it's going to be, natural form is going to be in the molecular form. At 1 atmosphere, how many decimal points did they give that to us? It's 2. At 1 atmosphere and 25 degrees Celsius. 25.0. Okay. Any guess on what we're going to use? Maybe the ideal gas formula? Okay. So we have PV equals nRT, correct? Do we have a pressure? Yes. Do we have a volume? That's what we're looking for. Do we know how many moles we have? Not yet, but we can figure it out, right? Because we have a mass. Mass divided by the molar mass will give us a number of moles. So we can compute N. We are given R, 0.0821. That's using atmospheres, Kelvin, liters, and then temperature. Temperature we have it in Celsius. We're going to need to convert it to Kelvin. So we're looking for volume. You could go ahead and rearrange this as volume equals nRT all over P. So N is the number of moles, right? We have a mass. We remember from our solution diagram before, if we have a mass, we divide it by the molar mass. That'll give us the number of moles. Everybody tracking with that? Okay. So I'm not gonna compute the number of moles. I'm gonna write it in the form of mass, 32.2 grams, divided by, what's the molar mass of chlorine gas? The mass of chlorine is 35.5. So the mass of chlorine gas, the molecule, is 71. So 32.2 divided by 71.0 grams per mole, that's going to give me moles, right? Then by R, that was going to be 0.0821. Just ran out of space here. And then by temperature. I'll go ahead and write it down below. Hate to cut anybody short with R is going to be 0.0821. Temperature, I've got it in Celsius, but I need to use it in Kelvin. So what is my degrees Kelvin going to be? Now I differ with the solution manual on this because they give us to the 10th place, right? When we add 273.15 to 25, we get 298.15. But since we're adding, how precise can we be? To the 10th place, right? So I use 298.2. Can anybody explain to me why it's not 298.2? I mean, the book says it's 298. That's what they use in the solutions manual, but I don't know why they would round it to 298. Either I'm just having a, senior moment, or they inappropriately rounded. And I've got first printing. I don't tend to trust that much anyway, so. I used 298.2 when I did it. So temperature here, Kelvin, 298.2. All over pressure of 1.00. Remember, the units in all of this are going to be taken care of because of the units to my R. Okay? So it's Kelvin, it's liters, it's atmospheres, and it's moles. Any questions on the solution, the setup? Okay, very gentle bobblehead. Most of you get this when you did it? Okay. Was there any tricks, any problems? If you use 298, that's fine. Okay. So this one was pretty straightforward, just the pure application of the formula. I'm going to assume that 9 and 10 get more into the stoichiometry, right? So, as someone noted, it's always in the application towards stoichiometry where it tends to get complicated. So let's just go right on to number 9. Silver tarnishes in the presence of oxygen and hydrogen sulfide according to the following equation. Okay, I'll go ahead and write it down here. I'm going to forego the phase symbols again, but that's a solid, a gas, and a gas to produce a solid and a liquid. Silver tarnishes in the presence of oxygen and hydrogen sulfide according to the following reaction. Usually, hydrogen sulfide is the limiting reactant. We're talking about tarnishing silver, right? We're going to have plenty of, generally we got plenty of silver, that's not the issue. And oxygen is in the air all around us, so that tends not to be the issue. So we have plenty of those reactants. It's going to be the hydrogen sulfide that limits it. It'll only tarnish when there's hydrogen sulfide available. If a silver spoon is placed in a container that holds 62.1 milliliters of hydrogen sulfide, at 1.15 atmospheres and 23 degrees Celsius, how many grams of silver on the spoon will tarnish? Hopefully you see that this is an extension of our stoichiometry, right, using gas law. We're going to be looking at how the silver that tarnishes relates to the available hydrogen sulfide gas. So if we were just using masses or volumes of concentrations, if this were liquid, but in this case, we're not dealing with a liquid, we're dealing with the gas. And so what I'm going to go ahead and do, just like we talked about yesterday, is go ahead and kind of use this slant to get me to moles, to get me to, the question finally says how many grams, right? How many grams of silver will tarnish? See, that's going to be our process. And it is a 4 to 2. Since I'm moving in this direction, my multiple is going to be 2 in my moles to moles. Okay, for the hydrogen sulfide, said that we have 62.1 milliliters. Now, what should you immediately do? What would I do rather than write 62.1 milliliters? Go ahead and convert it to liters, right? Our R value is in liters, not in milliliters, so you need to convert that to liters. So I just go ahead and write it as 0.0621 liters. At 1.15 atmospheres. And 23 degrees Celsius. It's 23.0, so we have to convert that to Kelvin, right? Okay. Multiply that by They are. So in our formula, PV equals nRT, N equals PV over RT, PV divided by RT, so I did this graphically this way. Since you're moving down, you're dividing. You're dividing this, P times V, divided by R times T. And that gives you 0.00294 moles. So this is N equals 0.00294. Almost 3,000th of a mole. So if 2 moles of hydrogen sulfide react with 4 moles of silver, then 0.00294 moles of hydrogen sulfide react with 2 times that much. 5.88 or something along that line. 0058, okay? So my stoichiometry relating those brings me to N over here is equal to 0.58. I've been asked for moles, and my translation is through molar mass. Since I'm rising, we're multiplying, right? So the number of moles times the molar mass of silver, 107.9, grams per mole. So I multiply 107.9 times 0.058 or 0.0058. Book tells me that I'm going to end up with 0.634 grams of silver. Okay. So here, if I had given you how many grams of hydrogen sulfide, you would have been able to convert how many moles by dividing by the molar mass. If I'd given you this in a liquid form and told you how many milliliters I had at what concentration, you could have multiplied those together to come up with the number of moles. Now, using gas law, given the pressure and the volume, and dividing that by R times the temperature in Kelvin, you can compute the number of moles. So all 3 pathways lead to the number of moles. Stoichiometry is the bridge that relates moles to moles. And technically on this side, we could work backwards as well. We could take the number of moles and compute either pressure or volume or temperature moving up. Okay. So 0.634 grams of silver reacts with 0.621 liters of gaseous hydrogen sulfide when that is collected at 1.15 atmospheres and 296.2 degrees Kelvin. Because that much at that pressure, at that temperature, is this number of moles. If I have a different temperature or different pressure, the number of moles I get for the same volume is going to be different. In the same way, the same number of moles is going to have a different volume. So, questions? On number 9. Are there any individuals in here who couldn't do the setup but see it now, at least? It's helpful, what you've just seen? The sense that you feel like you could do it again? We'll do number 10, and then I'd like you to pick one of the EPPs for us to do, okay? We've got one more half class like this tomorrow, and then we won't see each other again until the module exam next Monday. So, one rocket engine uses the following. So a common rocket engine uses the following reaction. They're reacting hydrogen peroxide. Basically, the stuff you put on your owie that bubbles up, it powers the rocket engine. Okay. If the rocket engine contains 2.89 kilograms, 2.89 kilograms of hydrogen peroxide and an excess, what is the volume of water vapor that will be produced when the rocket fires at a temperature of 500 degrees Celsius and 1.5 atmospheres. 500.0 degrees Celsius and 1.5 atmospheres. Just like I mentioned on the last problem, we could work it the other way around. If I gave you a mass to compute using the gas law, hopefully you can see from here that our solution diagram is going to look something like this. Taking a mass divided by the molar mass to get moles. 7 to, we're doing water vapor, don't let this confuse you, we're over there. 7 to 8, moving this direction, multiplying by 8/7 to get my second end, and then moving up from this point here. If I go ahead and label it PV and RT, this end is going to come from this end times a multiple of 8/7, so 1/7 more. Not going to go through and do all the math for all the different parts. Just wanted to primarily do the setup. So, is everybody comfortable that they could take 2.89 kilograms of hydrogen peroxide and tell me how many moles that equals? Compute the molar mass. It would be 2 times the mass of oxygen plus 2 times the mass of hydrogen. 32 plus 2.02, 34.02. Divide this kilograms by those number of grams. So make sure you take your, get your units right, or your scale right, and get the number of moles. From the number of moles, use stoichiometry to say that if 7 reacts with 8, then this many reacts with this many to produce this many. You'll get a second number of moles over here. This number of moles times 8/7. Then we have the number of moles. What we're going to do is work the formula up. If we're solving for volume, remember that if PV equals nRT, then V is nRT divided by P. At this point here, we will have an N. We know an R. Our T is going to be 500 Celsius, which is equal to what? 773.2 Kelvin. Okay, so that's going to be our T, and our pressure is 1.5. So ultimately, you're solving for the N value here, taking your ideal gas law, rearranging to solve for N, or solve for the unknown variable and plug in the knowns. The only thing they didn't give you was that N amount. That N amount came from that N amount. That N amount came from the mass divided by the molar mass. What about the EPPs? For those of you that attempted them. There's one in particular, at least try to get this set up before the bell rings. So was that 9 you said, Seth? 9, okay. Any other preferences than 9? Not you have to like compete or arm wrestle. 9's a good one. Big, long, scary equation, huh? It's too long. It's too hard. I should just stop now. Game over, man. Game over. Put her in charge. Okay. Sorry, that's a really old movie to you guys, right? I'm not going to read through all the reasons why, but there's the reaction equation. How many liters of fluorine gas? At STP would be required to completely convert 1 kilogram of titanium oxide into TiCl4. That's what this is. Okay. Okay. Mass divided by molar mass is going to give me N1, 3 to 6. My multiple is going to be 2. That'll give me N2. STP. So let's go ahead and rearrange it. Volume nRT over P. The N is going to be my N2. R is 0.0821. T is going to be standard temperature. It's 273, right? Pressure. So you have everything you need except for the number of moles. You get the number of moles using stoichiometry. Take the mass divided by molar mass to get the number of moles. Use the stoichiometry to give me my second number of moles, how many it needs to react with, and it says how many of these? Twice as many, right? Times 2, twice as many. 3 times 2 is 6. Whatever number times 2 is the second number. Plug that second number in. Here is the number of moles and solve for the volume in liters. From this point here, I could ask you how many grams is that? All you need to do then is multiply by the molar mass. I could ask you if it was in a certain number of liters, what would its concentration be? This would be the molarity, right? So once you get to these hubs, the hub being the number of moles, can branch off in a lot of different directions. You can tell me how many grams that would be. You can tell me at a given concentration how many liters that would be. And then for gas, at a given pressure and temperature, what the volume would be. I was going to ask you about 14. Where is that? He did? Okay. I heard 14. I wrote it up on the board. Like, I was going to go back to that. Where's 14 at? There is no 14.
This is the one that's under
The sodium chloride and the sulfuric acid. Yeah. Let's go ahead. I'll do that one on the right real quick. 4 minutes. Just do the setup. Sodium chloride and sulfuric acid. So we've got NaCl. You're making hydrochloric acid from salt and sulfuric acid. How many liters of HCl? Will be produced if 25 grams of H2SO4 are heated in excess sodium chloride Assume the pressure is 1 atmosphere. And the temperature is 350 degrees Celsius. Grams, molar mass, moles, moles, V, I use stoichiometry. I use 25 grams divided by the molar mass of sulfuric acid to give me number of moles of sulfuric acid. That is, relate them, and here it's 1 to 1, so it'd be the same number of moles, and then plugging that in to whatever that number of moles is times 0.0821 times the temperature, 350.0 plus 273.15 to the 10th place. So it'd be 3, 4, 5, 6, 23.2 divided by pressures in 1. And that'll be your volume. So again, mass divided by molar mass to give me number of moles. It's the same as this problem over here. It's exactly the same, just different math. Same process.